Okay, I think we are back. We are back, and we start with this. We had so in that case, if rho is the physical density of the mixture of the mixture, if the physical density of the mixture, the average density of the component, rho I will be Wi rho by 100. Similarly, exactly that we did earlier in the case of atom density. But Wi is the atom. Wi is the weight percent. Weight percent is right. W is equal to W percent weight percent. So this is one. This is and that is atom percent. This we write in weight percent, and this is the basic equation that we started rho and a by m, and then this will be mi and I, but the atom density of the component. This will be the atom density of the component. The atom density of the component. It is. I'm going to write it because we don't have much time. Let me share screen. So the atom density, Mi is in atomic weight, and so the atom density of the component is Ni. Ni, we shall have to calculate the Ni, and if we calculate Ni, we can go back to the other relation. Then we will get Ni equal to Wi rho Na. From this, this equation, we can get Ni equal to Wi rho Na by 100 Mi, where Mi is in gram atomic weight. Okay, now there are more complicated cases. Okay, with a substance whose component is specified by the chemical formula. We know that, say, if we have, say, in trigger reactor, we have zircaloy, okay, zirconium, and then erbium 166, erbium 177. So all this. So if you want to calculate the number densities there, it's a composition specified chemical formula. It has a chemical formula. We all know it. The percent by weight of a particular element is equal to the ratio of the atomic weight in the compound to the total weight of the compound. Say we have a compound. We have a, okay. So the atomic weight of the compound or the molecular weight of the compound. This with the compound, say we have a compound. This is a compound X, M, and Y, N. The molecular weight will be what will be the molecular weight of the molecular weight will be the molecular weight of this M or X to the molecular weight of the N of the element Y. Okay, so where Mx and My are the atomic weights of Xy respectively. Xy are the matrix, and percent by weight of the element, and so the percent by weight of the element, percent by weight of the element will be weight percent of X will be M, that is the M of Mx plus Ny multiplied by 100. And if it is My, then you will just put My here, My, My, this one, Mx plus My. So the same way, in these nuclear applications, the isotopic composition of the element must be changed through artificial means. Okay, that's a different case now. But anyway, so I hope that with the substance whose composition is specified by the chemical formula, say we have a compound like X and M, so the weight percent of X will be M of X and M and a molecular weight of this X and molecular weight of this Y and multiplied by 100. And if it is weight percent of Y, similarly, you will just put weight percent of My here, and this will be same then multiplied by. So this is the way that we can calculate the Mx and My, the atomic weights of X and Y, respectively, the percent weight by the element, and the percent weight by element X and Y will be you will use this formula. Okay. If we do some calculation, actually, really, then we will, we'll get the in-depth meaning. So, well, just remember this, that in case of a compound with X and M, this is the way that we get. In some nuclear applications, the isotopic composition of the element must be changed by artificial means. Like that, in a reactor, we have enriched the U-235. U-235, we shall have to enrich for a power reactor around something like 3 to 5% for a power reactor. The enrichment that we usually use in the nuclear reactor. And in a research reactor, it could be higher, but now because of the safeguard treaty and safeguard, so that people cannot manufacture, use this for using nuclear weapons applications. So that's why there is a forbidden limit of 20%. So in the research reactor, say in our research reactor in Sabah, it is 19.97%, just touching the net. So we shall have to enrich the U-235, because on the U-235 is the fissile atom. So that's all the problems. In that case, we shall have to take this into consideration. And for research reactor, it's 20%, let's say. For power reactor, it's 3 to 5%. And if you go for, say, nuclear weapons, it's over 90%. If you want to make atom bomb or, nuclear weapons, so that will be more than 8%. That's why it is so critically observed all throughout the world, so that no one can enrich more than 20% at the time. But some countries are trying, and once you have done it, no one can do anything. Like the Pakistan did it. No one can tell them anything. Israel, even though did not declare, but they have atom bomb. And now Iran is trying, they have gone up to, that's why, all efforts are taken against Iran so that they cannot enrich it and they say that we are doing it for our, they have power reactor. So for our reactor application, peaceful applications. But anyway, they have gone up to 60% now. Well, anyway, that's a different story. So this N, what will be the N? Here we get Ni. So the N will be summation of all the isotopes there and the number of density. Ni is the atom density of the ith isotope. This is the number of the ith isotope, that is U-235 or U-238, U-234, or say, if we consider other element, it has lots of, say, if we consider oxygen has lots of isotopes, at least how many? 3 natural, and there are 5 produced in the reactor, so almost about 8 isotopes. So this will be, at this end will be summation of all the, what will be the number density of the, say, oxygen. So you add up all the isotopes together and you get the number density of the oxygen, or you get the number density of U-235, number density of uranium, U-235, if it is U-235, U-236, so this will be the number of isotopes of uranium. Where Ni is the atom density of the isotopes, so introducing N from equation, this earlier equation, 259, and I from this we get this relation. And Ni is the atom density of the ith isotope, and now introduce N equal to our basic equation, N equal to rho M A, N equal to rho M A by M, and Ni equal to Wi rho M A by 100 Mi. So if you combine this using these two equations, finally computation involving these Mi, the gram atomic weight the Mi here, Mi is the gram atomic weight. Of course, I wrote it gram atomic weight, and then 1 by m equal to, we will get 1 by m. It's this one. This one. I'm not writing it since you are looking at the. We are sharing it. So you're looking at the page. So this will be 1 by m equal to 1 by 100 summation over wi and mi. So this you can calculate actually. You can put, you can go to these two relations and you put it together, you will get a relation like this. So this wi is the weight percent, this weight percent, and this mi is the gram atomic weight. And so you get 1 by m equal to this. The application of this formula in computation involving enriched uranium is illustrated in example 2.16. We will talk about 2.16, how we can use it. Okay. But before that, we just calculate, with this, use this with this. Example 2.16, I will finish today's lecture. But this one is a little bit, complicated to understand. We'll see it. What is this 2.16? And if you understand this example 2.16, you have already, I hope that you can calculate other number of isotopes also as well. Okay. For what are say normal unit density? 1. Compute here is the number of hydrogen molecules per centimeter cube, the atom density of hydrogen and oxygen, the atom density of hydrogen. Now, all the formula that we have discussed so far, from this we can calculate the molecular weight of hydrogen. What will be the molecular weight of hydrogen? Hydrogen, this is the weight of hydrogen plus oxygen. One oxygen is 15.994 and hydrogen is this. So this is 18.03 is the molecular density of water. So atomic density is 1 and molecular density, 1 gram per centimeter in gram atomic weight. So we all know it. The molecular weight, this 18.0 is the molecular density, is therefore, no, this is the molecular density. So the molecular density is therefore, now you want to have the molecular density of water. And this is rho is 1, and this is Na by 18.03. So this 0.002.03343 10 to the 24 molecules per centimeter. How many molecules? The number of water molecules per centimeter cube. We know the number, the unit density, not number density. The unit density of water is 1. So the molecular weight will be, we want to find the molecular weight, and the molecular weight is 18 point this, and the molecular density, one is molecular, this is molecular weight, and the molecular density, so you just multiply it by rho and A by molecular density. Like if it is atomic density, we just put that atomic number, and in this case the molecular number, the molecular weight, atomic weight and molecular weight. Okay. So that's how you see that this is the number of molecules per centimeter cube and the atom density of hydrogen and oxygen. Now calculate the atom densities. Okay, now we'll calculate the atom density. There are 2 atoms of hydrogen and atom in oxygen. The atom density of hydrogen NH. So this NH will be number of atoms will be 2 into point. The molecular density is whatever the molecular density we calculated. 0.003, 0.033 this. So this will be there are 2 atoms of hydrogen. So this is the molecular density, and 2, since there are 2, so you multiply this by 2, then you get the atoms per centimeter cube of hydrogen. And oxygen, we have this 0.03343 molecular weight. Then this is the number of similarly you get the number of oxygen is 0.03343 because it has only one, so you multiply it with one. So you get this is the atom per centimeter cube, atoms per centimeter cube of water at normal temperature. Actually, the relative abundance of hydrogen. Now, say what will be the relative abundance of neutron? It has neutrons also, and the gamma of neutron is 0.015 atom percent. So you just multiply this 1.5 into the 4 into the number of hydrogen. We have got the number of hydrogen here. So you multiply the number of hydrogen by the abundance, you get the number of neutrons. That is the in the heavy, if it is heavy water. Heavy water is just hydrogen and neutron together. So we call it neutron. So the number of neutron will be these atoms per centimeter cube. Well, I hope that you understand. From this simple case, now you can understand how to apply the equations that you have seen, and you can derive those equations just by using the three basic equations. And and the second problem is a certain nuclear reactor is fueled with 1500 kg of uranium rods and reached to 28%. It's a research reactor, 28% of U-235. The remainder is, of course, U-238. U-234 is very, very little press, so you just ignore it. So the density of uranium is 19.1 gram per centimeter cube. So how much of uranium is in the reactor, and what are the atom densities of U-235 and U-238? It's very simple, because how much 20% means that 20% of the total uranium mass is U-235. So the mass of the uranium-235 is 300 kg. This 1500 kg multiplied by 0.2, it is 20% at least. Okay, this is very simplest case. And now the atomic densities of U-235 and U-238. U-235 atomic number is 23.05. So for atomic density of U-235, we just use this 20 weight percent. This is 20 is weight percent, and 19 point, this 20 is 100, 20%. So this is 19 point rho, and a rho is 19.1, Na is this, and this is atomic weight of U-235. And you get, this is the atom, this is the atoms per centimeter cube of the fuel. Okay, so it's very simple, right? Rho Na, and since it is 28%, you just multiply it by 28%, and Na by molecular, not molecular weight, by atomic weight. Okay, because the atomic weight of U-235 and U-238 we know. But if we consider that molecular weight, then you will add these two and you will get the molecular. But here we are concerned with the atomic. So similarly, U-238 percentage will be 80 by 80%, 19.2, and then this is the atomic weight of U-238, and you get this for the the U-238 is present. What are the atom densities of U-235 and U-238? So you get the atom densities of U-235 and U-238 is this. So you can calculate the atom densities of U-235 and U-238, and you have only what a certain nucleus fueled with 1500 kg of enriched uranium. You have only uranium here. But actually, in the nuclear reactor, is it only uranium? It has lots of other stuff. It has the cladding. It has the fuel meat. The fuel meat has the fuel meat has lots of poisons and lots of other moderators and other things, like say in our trigger fuel meat. What we have uranium 235, uranium 238, and then what else we have? We have zirconium hydride. Very complicated thing. Zirconium hydride, zirconium, and then hydrogen, and this is combined together, zirconium hydride. So these are very complicated things to be considered. You know, when we consider zirconium hydride, okay, I'm coming to this next. And then we have erbium 166 and erbium 167. So all these are, that is zirconium and hydrate, that is hydrogen. Zirconium is there, hydrogen is there, and erbium 166 and erbium 167. Why this has been like this, we will discuss. It's a very interesting physics of nuclear reactor. Well, very interesting, because we have intrinsic safety. That is, if one wants to oxygen, two oxygen atoms with one uranium. So the density has come down to 10.5 gram per centimeter. And if the uranium is enriched to 30 weight percent in U-235, what is the atom density of U-235 in the well? So it has make it a little bit complicated. Okay, so I will. Okay, I will give you a simpler. It is done here, but I think it makes it very complicated. So what do you do for first compute the atomic weight of the uranium mix? How many time we have? We have time, inshallah. We can finish it. After we finish it, the class is over. So let's go in steps. If we go by steps, the first step, first we compute the atomic weight of the uranium. Come on, please. Please unmute. What uranium is. What will be the atomic weight of the uranium mix? Okay, and this we can learn by 1 by m equal to 1 by 100 summation wi by mi. Summation wi by mi, which is this equation 265. So 1 by m, 1 by m equals to 1 by 100, 30%. The enrichment is 30%. So we put 30% and then uranium, atomic number of uranium, and then plus 70%. It is U-235 atomic weight, 235, and U-238 atomic weight, and you put, and then you add it together. You add it together, then from this you will get, from this here you will get n equals will get this M equals 237 to 37.141. Okay, this is step 1. And the step 2, molecular of uranium dioxide. This is step 2. Molecular weight of uranium dioxide will be 237.141, which we have calculated. Molecular weight we have calculated 237.141 plus 2 into oxygen 50.99994, which will be equal to 269.139. Okay, so this is the molecular weight of uranium dioxide. Step 2, and this step 3. Step 3, percent of the weight percent of the uranium in uranium dioxide. Percent by weight of uranium dioxide. So this will be weight percent. Weight percent will be n of mx, m of mx plus m of my, m of my, and from this this multiplied by 100%. So this will be something like 88.1. Okay, I did not do the calculation. You will do it 88.1%. This will be 88.1%. So the percent by weight of uranium in uranium dioxide is 89.11%. You just use this formula and you can calculate it. Okay. This will be 237.1 mmx. 237. This is like one more step. 237.141 divided by 269. Uranium altogether actually 269. 269.1139 multiplied by 100. So from this you will get this is 88.1%. One step more. Okay, so this is step 3, and finally step 4.
Sir, teacher লেখা
237.141 by 269.139. 269 is coming from U235 and U238. Okay?
Yes, sir.
Can you see it now? It's
Yes, sir.
269.139, 237.141. 237 we calculated M, and this 269 we got from U235, atomic weight of U235 and U238. Add it together and then percent, of course, percent. You got it. Okay, so I hope that you get these steps. You just try to understand the steps. Okay. So the average density of the uranium is this is step 4. uranium is 0.881 into 10.5, the density of uranium, and 881 we calculated. This is 88.1. So this is, if you take the percent, then this will be 0.881 into 10 to the power 5. This will be equal to 9.25. This will be the average density of the uranium is 9.24 gram per centimeter cube. Maybe you can do it in other ways also, but this is, this is the most logical way, just to make you understand that the formulas that we have written, we can use these formulas to calculate a little bit complex fuel material. So this is 9.25 gram. Average density is 9.25 gram. So the density of uranium density of U235. I just write U5. You understand that U235. 35 is how much? 30% is U235, right? So it will be 0.30 into 9.25, 9.25, which is equal to 2.78 gram per centimeter cube. And if we know the gram, the atom density, we can easily calculate. If we know the gram, we will just multiply it. So the atom density of U5. Yes, yes. Okay, so I hope that you all of you understand this. I'm getting a view echo. Someone unmute, please. The atom density of uranium is 2.78 gram per centimeter cube. So if we get the number density of the U235, in that case, the number density of U235, the number density of the U235, if you know the gram, you just multiply it by the Avogadro's number and then by the atomic weight. So you get the number density of the atom density of atom density, or what about the number density, atom density of U5